Good morning, good evening, good afternoon, everybody. Welcome to the November edition of the Eerie community meeting. Today we have Lei presenting some of the work on metal support in Eerie. And well, it's been and I think some of the new HAL work. So it's something that we've been talking about for a while. So quite excited to see the presentation. After that, up to you, Lei.
Thank you, Rag. Yeah, I have been actually pushing this for a couple of times, so finally make this happen. Yeah, gonna talk about metal support in Eerie, but before going into the slides, maybe go to the architecture graph, talk about what I'm gonna touch. So this is the whole Eerie structure pretty much. Today's talk is mostly centered around this part, where you see this hole and a bunch of implementations. We actually don't have metal there, should update the graph to include that. And this runtime part is actually the VM executes instructions that calls into whole APIs pretty much. It seems like lots of like pre-processing with compilers that to generate the whole instructions, whole commands. With that said, I'm going to back to the slides. So this is like where things are right now. So first, need to talk a little bit about the Eerie whole in general, because this metal is effectively a implementation of the whole hardware abstraction layer. We call it drivers, which is just like mini implementation of the whole on top of particular GPU API pretty much. So it starts with like the CPU, GPU host device architecture. This is like fundamental pieces that the whole Eerie based upon that we have the CPU side handling scheduling logic and GPU side doing kind of like dense compute and stuff. No, I'm using GPU here because I'm talking about metal. Effectively, CPU itself can also be treated in the way GPU are treated with the host device split. But I won't go into too much details there because today is more talking about GPU side. This structure is like rooted because we have this real physical world that we have like GPUs, discrete GPUs that sit over the PCIe bus where you have like physical separations there. CPU basically talks with GPU over the PCIe, and that separates the memory hierarchy and compute units onto separate walls, especially true for non-unified memory cases. So that means like when you want to get some data from CPU to GPU or vice versa, that you need to actually do a bunch of like cache controls. It happens sometimes implicitly for you by the API for usability purposes. But as we push for more kind of like performance, it's showing its limits. Sometimes we want to do it by ourselves to precisely control. On Apple side, things are more aggressively moving to SoCs. So we have like a unified memory on the right. Basically, CPU and GPU are now in the same die that these are just different IPs. They kind of share L2 cache or some low-level caches and talk with DRAM in that way. But still, like the architectural the structures that like CPU, GPU maintains its own, for example, MMU, IO, MMU, those kind of things that you still kind of needs the structure and the scaffolding happening for discrete GPUs where you want to make sure data get visible on some IPs. You need to do cache management and stuff. Like you can sometimes do probing and do snooping, but that comes as a cost and sometimes. So with that said,
another good way to think about this is it's not just memory, but also like clock domains and power islands and things like that. So even in systems that look like they're the same thing and they're sitting on the same SoC, usually they have different controllers, different latency requirements, different cooperation mechanics if you're in an OS with thread schedulers versus a GPU with time slicing. So it's all up and down the stack.
Yeah.
People will often pick one thing and say, oh, but they're the same. But then, there's 20 different systems that are slightly different. So
yeah, that's a good point. I know, like for Mali GPUs, they actually use different clock domains and stuff for different parts, so that even the same CPU, even the same GPU were like different. I think texture stuff are kind of in a different power domain. Yeah, good point. Going downwards, I mean, there are like going through the journey, like there are lots of like ways, platform specific or vendor specific, that are trying to reflect this reality and trying to expose this reality to programmers via some APIs. Notably, platform-specific ones, Metal, for all Apple devices, which we'll be talking about today, and also D3D on Microsoft territory. And then there are some vendor-specific ones, CUDA, we all know about that, and ROCm from AMD, one APIs Intel is pushing on recently, trying to have a unified story for their IPs. And some of them are kind of like been there for a decade or so, like CUDA and stuff like that. And there are recent developments, I mean, 5-6 years ago, like Vulkan being put up by the industry, trying to gain experience, leverage experience from the past decades or so, trying to encode that experience into a new fine-grained, low-level explicit control APIs. It is meant to be like cross-vendor. So it, by design, bakes in lots of like support and assumptions how you can do things in a like platform agnostic way. I think in that way, like Eerie's hardware abstract layer faces similar requirements that we need to basically support different implementations on different platforms for different vendors. So and we also, because with the domain we are trying to handle here is like we have lots of like higher level information that can be distilled into very fine-grained, low-level explicit controls. Something like that means the requirements and the needs from the Eerie's hardware abstraction layer is similar to what Vulkan is actually already encoded. That means like we on Eerie side adopting a Vulkan compute-like API surface, but it's much more simplified to like remove less of the things that are not necessary, because they are just there for standardization purposes, so like trying to cater to lots of vendors, especially on the graphics use case side. Again, note this is also for driving CPUs, and we have this unified host device architecture and having the whole layer for abstracting basically dense compute, communication, stuff like that. But I'm not gonna talk extensively on that. And then this whole structure expect Eerie compiler for basically constructing the API calls, because it is so explicit, so low level. You can do it manually. You can call like the Eerie whole C API, but typically it's tricky and it wobbles to get everything in a nice way. We have the stack trying to use compilers to distill high-level information and to have us being able to do very good async scheduling and fine control memory usage and control object lifetime. So some of the key points from my point of view that the Eerie whole would want to do, and the goal is basically, I mean, we know like nowadays basically compute is way ahead of like memory capabilities. Compute can double, triple in a few years, but memory is like still memory technology is still lagging behind pretty much. So efficient memory management is really a key for lots of the workload there, especially for LLMs. You know, like pretty much so demanding on bandwidth and memory. So in Eerie, we want to enable efficient memory management. That is basically explicit memory system modeling, like you have a hierarchy on the CPU side, you have hierarchy on the GPU side, and how you like do cache, flush, cache invalidate, and how to actually move data across them in what kind of like visibility, what kind of like memory heap or whatever. And that can and should be all precisely controlled. And in order to make Eerie play nicely with other systems, we have pointer importing, exporting basically for exchanging buffers without copy, zero copy stuff to support like pre-processing like other applications or layers and post-processing stuff like that. And we don't want to actually do lots of like small allocation stuff. And we use compilers to plan and do aggressive allocation packing and slicing, pass in the pointers or the descriptors, and then do a part of it, do a slice of it basically. So the whole model might see all the constants packed in one allocation and then get allocated and then streamed in at the beginning, or even begin the model running and stuff like that. And then memory side, then compute side is actually we want to go as async as possible, pretty much, and that is or the execution. Actually, another step forward is actually making the allocation also async. There are work going on right now. I think the next step will be trying to really enable that and how all the backend going towards that territory. Right now, it's kind of like in a irregular state that some backend support it, some backend still does not. We use one single mechanism for do synchronization at the coarse-grained level, that is Semaphore. Basically, on Vulkan is time-lapse Semaphore. On Metal is like shared event pretty much, that is does all the directions from host to host to device, from device to host to device, and very flexible and powerful. I'm gonna talk more details later about that. Another thing is like we really want to drive down the API driver OS cost, because these things like you can go async and then like let the GPU always be busy, and that requires you to actually give it to work in a large chunk of things, and also all the things like driver managed representing the GPU objects has cost. We want to do it once by like hoisting or packing or batching various ways. And the API, especially on the Vulkan side, really encourages that. It requires you to actually set up pipelines, set up all these kind of things in advance, do a kind of static planning in a sense that you can actually reuse the object created as much as possible. And again, with all the global information, we can do really good explicit GPU object lifetime management with compilers. This all happens and are enabled by having compilers on the upper layers.
Yeah, and a good point of reference for some of this stuff is like orders of magnitude wise, like what a lot of people will look at when micro benchmarking of like an MNIST model or something might do 30 or 40 commands, but the LLMs we're looking at might do 2,000 to 3,000 dispatches. And so even saving 100 nanoseconds per dispatch of overhead, that can be milliseconds of time that is otherwise just wasted. And so these kind of things, the batching and the aggregation and the reuse and stuff like that, when you're fighting for microseconds really matters.
Yeah, it's that
easy to forget when looking at just a single dispatch or something, just how much overhead can scale out in an entire model.
Yeah, especially it's like all of this intensively read-write memory and stuff. Like you just like how so many different, basically the same layer replaces so many times. And as said, like basically death by 1,000 cars. That's 1,000 cars. If you don't get it nicely on the small details, gonna accumulate and be slow. By the way, feel free to interrupt me anytime if you have questions. So with that said, I mean, we talked about the whole and talked the key design points and the goal we are trying to achieve basically, and then real going to like more like the code and the real concrete implementations and the whole API surface that's like a higher level. The whole basically has a few core responsibilities. One is actually doing GPU discovery and enumeration. For discovering capabilities and stuff. That is reflected in Eerie at the API level with the Eerie whole driver and the Eerie whole device. I will go through this concept with concretely how Metal side implements it. So, but this is just like an overall picture. And then the next big thing is like a resource management, two parts. One is actually memory side. We have a Eerie whole allocator, basically taking ownership of the buffers created, device buffers created, kind of like swappable and exchangeable, where like you can have multiple allocator implementations and layers of whole allocator implements and stuff like that. and then Hall buffer, which is like for continuing data. Another thing is like compute pipeline management. That is reflected by Eerie Hall executable, for like think of it as like a kernel source code, compiled kernel source code in ISA form or whatever, and a whole pipeline layout, which is pretty much like executable plus all the bonding slots and the arch points if needed for resources stuff, like detach from the real concrete resources, that you can have different buffers swapped and with the same executable running on kind of like different layers of stuff. And then the third is pretty much execution and synchronization. Execution is mainly represented and captured in the Eerie Hall command buffer, which is essentially recorded commands to be applied on device and stuff. And then Semaphore mean coarse-grained synchronization mechanism. Devices where like you do all this kind of submitting execution to the device and do synchronization. This is just like an overall API surface explanation. It's not extensive, but want to give a general picture first before going into details. The next step would be I'm going to talk about Metal Hall driver and how they are implemented against the Eerie Hall. So a little bit about the Metal API. This is the only GPU API natively supported for Apple platforms, including macOS, iOS, and like other kind of OS, TV OS, or whatever. But the primary focus we have right now is mostly for laptop and mobile. So please do macOS and iOS there. My feeling is like it's a blend of the old implicit style and the new explicit style, where like, for example, you have you can control like in the command buffer whether you do serial dispatch or concurrent dispatch. Serial dispatch means like the driver implicitly inserts a barrier for you after its dispatch, so make sure memory are visible, and then you don't need to care about that. But concurrent, you need to actually handle the synchronization by yourself. And then like whether you have retained resource, make sure actually once you launch something, all the resources are captured implicitly by the driver to make sure they are not going out of life before they are done using. And then whether you have automatic history tracking, like this buffer is written by some previous dispatch, or it needs to be read by the next dispatch. Unlike the driver, whether you want the driver to do that kind of tracking to make sure, okay, the second dispatch won't be launched until the first dispatch is done writing. In Eerie, pretty much we only use the explicit style, means like we do concurrent dispatch, we do unreturned resources. I mean, in the sense like the driver does not return it for us, and then we don't rely on driver hazard tracking. It's all the things are explicitly explained and like explicitly planned at the Eerie level, where we do our own barrier and synchronization. We do our own object lifetime tracking and to make sure they are not tripping on each other's foot or whatever. So, Scott?
So in Vulkan, there are Vulkan validation layers and things that will let you do this kind of freeform tracking yourself. Trust me, I know what I'm doing, but then you can opt into the layers that will check it. Is there a kind of similar thing in Metal here where if they have the code to do the tracking themselves, it seems like they could also validate your own tracking?
Yeah, in Metal, you have validation layers and stuff like that. I mean, you can enable that. I'm not 100% sure the extensiveness of the validation layers, validation facilities on Metal side. I do use it actually to capture some issues, but thus far haven't actually run into like kind of like resource hazarding issues. I think it should be able to do that.
Yeah, unfortunately, a lot of their validation has behavioral changes. So the cases where you'd really want it the most around the resource hazard tracking and stuff changes the resource hazard tracking. It's still cool and useful and stuff, but can. I think they're missing the composition style that Vulkan has in terms of being able to lightweight overlay and interject API calls.
I do have like command line options to let you kind of fall back to serial dispatch, for example, fall back to trained return resources automatically as they're tracking, more for the purpose that it is easy to debug issues. You can turn it on to see whether it fixes the issue. That gives you a hint whether that is likely the category or bugs you are running into. There are like command line options and driver controls on those fronts for debugging purposes. Continuing with that, basically we have Object-C and Swift language bindings to call into the Metal API. In Eerie, we use the pure Object-C flavor that. So we used to have a V1 version of the whole driver written against the previous Eerie C++ whole that was remote. The current one is pretty much rewritten entirely against the Eerie C whole now, earlier the year. The surface, the support is kind of aiming at Metal 3, which is launched earlier 2022 or something, I cannot recall. Pretty much like prevalent current macOS and iOS, given the speed like things got updated on Apple devices. For macOS, we primarily support Apple Silicon because unified memory that is quite similar to iOS. The like old generations and devices are phasing out, and they have quite some differences regarding how you handle memory and stuff. No plans to support them unless there is a really good necessary demands. It's fully functional right now and enabled by default for Apple platforms if you compile, and also shipped in the Eerie runtime Python package for Apple platforms. And we have been collaborating with E from Apple, doing development phase. He wrote some very nice and great demos that is now open source in the given link. You can feel free to check them out. We have been working on GPT-2 and stuff earlier. There might be some issues recently. Something might be regressed. We are still hunting the bugs and to make sure things are running. Also on Llama 2 and stuff, our side, that are imported from PyTorch. So I talked about the Eerie Hall struct, and this is the pretty much conceptual mapping on the Metal Object-C protocol level. For drivers, we don't have a correspondence. It's like more like software construct, and the device, you have MTL device, command buffer, you have MTL command buffer. Semaphore, you have shared event, stuff like that. Buffer executable have mappings. Because of the Eerie Hall is kind of like modern GPU API abstraction. So in a sense, maps nicely to like modern GPU APIs. So you can see like lots of the core pieces have direct mapping for Metal side. So that makes the implementation kind of straightforward. Unlike some like for example, if like Semaphore on the CUDA side need expensive emulation where because we don't have that kind of powerful mechanisms on CUDA where you have co-event, which is only meant to be actually synchronizing between device and device and device to host. Lots of like efforts need to be put into to see how I actually bring it to the powerfulness of like Semaphores expected by Eerie Home. Going through like pieces by pieces, the first thing is like basic driver and device. Driver is kind of the factory that you discover and create devices. This is implemented by Eerie Home Metal driver _T. Again, there is no direct Metal API construct. At Metal API level, you create device directly. So this is a pure resource object on the host side for object tracking and resource management stuff. At the beginning, we pretty much return all available MTL devices for during the driver lifetime. So once you created a driver, you can expect that devices have the same pointer throughout its lifetime. That is not guaranteed if you just like create device again and then destroy device and then create device again from the metal side.
One nice thing is the whole driver concept is an optional feature of the HAL. So if the user knows exactly which device they want, they can just wrap it. And so there are cases like on embedded systems where you wouldn't have a driver structure because you're just wrapping a piece of hardware you own. So it's kind of nice to be able to separate these versus what Metal does itself, where it just kind of is a static method somewhere that you just magically instantiate things.
Yeah. The main part is actually the device. The device is the logical context pretty much for all the device resources and allocation, execution. So we have ID MTL device pretty much in Metal for that. It owns various kind of GPU resources, pretty much everything. For memory, it is through another layer of like abstraction with allocators, but still fundamentally is owned by the device. And all the executables and the compute pipelines derived from it, and the command buffers that are recordings of the commands to be issued to the GPU. These are all tied to the lifetime of device. I mean, you can create them in the middle or destroy them earlier, but fundamentally they are found by the device. In Eerie, that it is assumed that if the device goes destroyed, or the other things with associated is not valid anymore. So, and then for now, we have each device now only use one command queue for execution. There were surface area in the API that we have had plumbed through trying to support multiple queues, but that is not fully flushed yet. And we have, for the current implementation, each device has only one command queue. It also has associated dispatch queue for running async workload from Semaphores. I will talk more about that when talking about Semaphores. Basically, still a kind of direct translation because of the likeliness, because of the similarity between the Eerie Hall and the Metal API on this level. Driver device at the top level kind of like context each thing you play with when doing stuff with the whole. Under the memory side, we have allocator and a buffer. Allocator is like this whole allocator. There is a host side allocator in Eerie. If you read the code, that is more for like this, like Eerie underscore allocator underscore T. It is for like host side memory and management allocation. You see that like in host side, but that is mostly for whole implementations. Use the host allocator to grab memory on host side for all this kind of host GPU object on host side. So it can be confusing if you are just like getting started on this, but that's the difference. On the device allocator side, it creates device buffers. Again, allocator does not have direct Metal API construct, pure resource management on the host. It allows to actually group all the buffers and stuff, and it created, and also you can have multiple allocators if you like. And in Eerie, the idea is like we pretty much can have each hole doing simple allocator and have like shared like capabilities like caching, sub-allocation, being done in an upper layer of allocators, the layer on top of the native allocator implemented by the various whole drivers. And then again, with the compilers on top, that you can plan and pack buffers in a great way. Sometimes some of the necessary tricks you pull in the allocator in other systems might not be that essential here. We again, as said, like the current implementation on the Meta side is like just a direct allocator, no caching and sub-allocation. So it's pretty simple. If you ask a buffer for it, it will create a new buffer for you, and not doing anything smart there. The allocator support import buffers for interoperation with other systems. Now, exporting buffer hasn't been implemented. On buffer side, this inherits the kind of explicit control we have on Vulkan compute and the Eerie Hall side. It wraps a ID MTL buffer. There are lots of things that you can control it, like placement and visibility. These are going into some fun details of Eerie and how the memories, the buffers modeled. For example, the device local but not host visible is using MTL resource storage mode private. And on macOS, especially for non-unified memory, we have managed resource that meaning something, and that is used for like device local host visible. That requires to do explicit cache management. Pretty much anything else used storage mode share. There is also like additional signals you can give to the driver, like whether you are reading or writing this buffer, and what is type is uniform buffer or a storage buffer, stuff like that. I will not go into that much of details. Feel free to check out the code if you are interested. All these things are in the Eerie whole top directory. There are various header files, but it has put really great documentation as a comments on top of the API. So gives you quite clear semantics explanation on various bits. So, but it might assume you have some good GPU low-level knowledge to really understand things there. So, continuing. By the way, feel free to interrupt me. I might be going too fast. I don't know. How much time do we still have? Oh, okay. So computation side, we have command buffer, which is a software construct that you use to as a container to record sequence of GPU commands to be applied and submitted to GPU. This is just like creating the recipe, not yet sent to the GPU yet for real execution. There are direct mapping on the Metal side, so it makes things easier. MTL command buffer is the one we are using. It's one shot. You create it once, and then you use it, and then you discard it. My understanding that this thing is meant to be also lightweight on the Metal side. So there are also MTL indirect command buffer meant to be actually created and created once and replied multiple times, and that is going to be needed once we actually move the whole side to be doing reusable command buffer to further drive down the driver and OS cost as chatted earlier as one of the key points of the Eerie Hall. There are differences here actually between the whole and the Metal command buffer. The whole command buffer is actually a modeling and like using the Vulkan compute recording style that you can directly record both memory and dispatch commands into the command buffer. Metal doesn't do that directly. It actually has additionally another layer. You need to create a bleed, which is for memory EMA operations, and compute encoders to encode commands into command buffer. And these split compute encoders can only encode command of that category, meaning you cannot do compute dispatch encoding in a bleed encoder, vice versa. So, and you need to continually switch between the bleed and the compute encoder if you are doing this kind of hybrid encoding style. This matches. There are also mismatches between other API features, like on the Eerie side, we have barriers, which is fairly extensive. You can have lots of bits controlling where you want to synchronize between the memory and make memory visible on a certain buffer or whole memory or some other features like its host device or things like that. The Metal surface area, API surface area on this front is much less. So these are trickiness when bridging the gap and doing the implementation of the Eerie Hall command buffer on top of Metal. So the implementation right now, trying to fix this gap, bridge the gap is done in 2 steps in encoding essentially, using a linked list of command segments. Basically, first we when we call the command buffer begin and start recording things, we don't really do recording into the MTL command buffer directly. It actually keeps the information sent by the API, by the Eerie hall, keeps them in a in-memory linked list, keeps all those informations and associated data. There are some trickiness here, like some of the things are stateful, like you are keeping push descriptor set, keeping push constant, get iterated, and then once you are trying to keep track of all these kind of commands, you need to take a snapshot of the current state, and then encode that into the in-memory linked list of command segments. When you call command buffer end, which means they are ending the recording the command buffer, we go through the linked list of command segments, and then record the contents into the proper MTL command buffer. This gives a chance to actually look the command segments before and after the current one, so we can actually do things proper. Like if you have the previous command is actually a bleed, or actually memory command. The following command is a compute command. That means, okay, you need to switch the encoder. You can do that. When you have a linked list of the command segments, gives you complete picture of what the command buffer looks like, and it also gives a chance to fix up some of the missed matches between API features, like barriers. Like you have kind of encoder switch, means naturally you need to synchronize there, like using fence or other using event. Like we are now using event. The recommended way is pretty much using fence, but that might mean creating lots of fence objects. That's how we are doing one MTL event.
I think this layer is a good example of the tension that is often seen at layers like this, where if you're someone who's just like a metal developer, you're like, oh, just give me the metal things as it wants them, blit and command encoders and stuff. But a good way to think of command buffers as we treat them is it's a compression layer, and it's a stable API target from the compiler. And so we're not optimizing for using metal in the way metal is designed. We're optimizing for the smallest possible binaries that the compiler produces, the simplest possible binaries for the compilers to produce, the most unambiguous ordering of operations. And I think like the implementation you have here, which is kind of the same we had to do on the web GPU side, because metal is extremely religious about this blit and compute encoder difference, even though it's demonstrably not necessary. And they infected web GPU with that. So we have to do the same thing on both sides. But this is a good example of an implementation where just because our HAL command buffer has a certain API and set of semantics that's optimized for the compression and stability and things like that, doesn't mean that has to match one-to-one with the underlying API, that we can still relatively easily adapt to these more complex APIs that have more strict requirements. The difference there being we really are optimizing for the compression and the stability from our perspective, a user's perspective. And the targets that require that additional work are the only ones that pay for that. Whereas when we're going to Vulkan or Direct3D or on CPU or CUDA or ROCm, which have completely different semantics than any of these, we're not emulating blit and compute encoders from the metal API design on top of CUDA, for example, which has no concept. And so I think this particular layer is a good example of where just because we have the HAL and the API doesn't mean that we can only target device APIs that follow that model exactly. So I think this particular one, allocators and stuff are all whatever, but this is where it really demonstrates that level of indirection that we have there.
Yeah, makes sense. I think regarding performance, pretty much because we have the compiler and all these things to clean up and issue the commands in a very clean way. It reduces at least it reduces the amount of things get recorded. And once we have reusable command buffers, even command buffer composition and recording will be a one-time thing that I'm not that terribly worried about the performance on this. So this is the execution side, and the synchronization side. As said, we have Semaphore one mechanism to roll them all pretty much on a coarse-grained level. We have barriers inside the command buffer is studied. That's like more fine-grained control. Semaphore is more like controlling multiple cores on the CPUs or GPUs to synchronize between IPs and stuff like it. It is a powerful mechanism. You can do in-device synchronization there too. There is a direct mapping on Metal, which is MTL shared event. Under the hood is conceptually you can think of this this is ever increasing unsigned 60-bit value, where it's like one side can signal a value to some larger values, and another side can wait on a value to be reached and do the synchronization in this way. It loves like wait before signal, multiple consumers wait on the same signal or whatever. It's very flexible and powerful. Fortunately, we have direct support, direct mapping on the Metal side. This is naturally supported by the OS driver and all this underlying stack. The CPU wait would need use additionally dispatch Semaphore and requires registering callbacks on dispatch queue to wake up current thread. That's kind of like fine-grained implemented detail. This is also the way recommended by the Apple tutorial and various docs, so it's well-known solution.
Yeah, this is another good example of that point where what we treat the semaphores as, and as we use them from the compiler as we're producing models, we're also importantly using them and exposing them on our public API. And the kind of thing that usually we look for here is the metric is not, you know, direct mapping or on particular backends, you know, in the case of like the dispatch semaphore needing a GCD kind of operation to wake, is not a particular backend optimizing the number of host wakes, but globally reducing the number of host round trips. And the semaphore model, the timeline semaphore model that kind of Direct3D and Vulkan and Metal and stuff have all adopted is really optimized for that case of reducing the round trips of when you're in a library and you're one library within a system potentially used by multiple wrappers, which might be like model front end kind of wrapping layers, which then is wrapped in an application that might be doing its own asynchronous stuff. This allows us all the way through the stack to kind of coherently model this stuff, get it all on device, get it batched, get it in flight. Even if it does require occasionally, you know, a host interrupt wake up to emulate something like the CPU wait in these cases. So even though our API kind of is fully timeline semaphore based, even if under the covers on particular backends, we have to do with some additional wakes or, you know, CUDA launch callback kind of stuff to emulate it. We're paying for it in a much smaller set of cases than if every operation we performed needed a full host round trip, or, you know, was synchronously blocking, or you know, the kind of classic case in ML frameworks of just launch an STD thread and sit in a for loop, you know, around your model or something like that. So I'm trying to reason about some of these things of ways to call out in the documentation that like this is a concept that we target, but not necessarily a requirement of the system under the covers. And really until you see like a full asynchronous, you know, like what we're shooting for here is pipelines of multiple models running concurrently within a single process, potentially multiple processes and running against the same devices. And then you see the scales of the LLMs and other models you might be wanting, you know, associated models you might be wanting to run in the pipeline. You know, sometimes it's easy to just be like, oh, if I could just have a CUDA event and just signal and wait on a CUDA event, everything would be great. But that never scales up to that full kind of application set. And so we've kind of front loaded and optimized for that set. And then that means if all you want to do is dispatch one thing and wait on it, it does feel like, you know, an extra 10 or 15 lines of code. But those, you really shouldn't use Eerie if all you're going to do is dispatch one thing.
I think it comes to the original picture. I mean, the architectural picture I showed at the beginning, right? Basically, we are talking about the Metal implementation of the whole. That's like a zooming in a small subsystem of the whole picture. Always keep in mind there is like lots of scaffolding, lots of like things we have built up, like in the basically in the like showing really quick that So you have so much like things on the top that trying to optimize things in a big picture way. So we can do the goal is to be trying to get all the big picture and the important things really in shape, and then having this Eerie whole layer service into that, and then the whole implementations. I mean, doesn't need to be super clever. It doesn't need to pack all the tricks inside of the whole implementation. It becomes a kind of thin layer. I mean, as Ben said, sometimes we need to do some emulation. Sometimes we need to because there is no direct mapping because different systems API is different. You are bound to do some emulation, do some not direct mapping somewhere, but it's kind of relatively straightforward still. I mean, this is still a subsystem, and this is the whole picture that we are shooting for. These things work together. So I think I have this slide. Next is basically compute pipeline. This is like the shader kernel, the ISA shader kernel, and then how you manage such resources and stuff. Basically, executable is like if you look at Eerie source code, that's how executable is kind of a compiled program archive in the ISA form. In Metal side, it is actually bundling quite a few things: MTL, MTL function, MTL compute pipeline, state, all those things, and associated information like layout, thread group size, and stuff. Right now, basically, also we have some built-in executables for polyfilling some whole features that are not directly mappable, like flexible Eerie whole command buffer fill update buffer. This part is something that I think we need to improve on the Metal side, because like the way right now it works is basically we have two ways pretty much. One is actually directly embed the Metal shading language string into it. Another is actually we do offline compilation to compile the MSL source code into MTL library. That is actually the preferred way to go. You can actually go even a step further with current generations and the improvements for Metal to sort of like directly embed the final isolation thing into the executable. But I haven't been gotten time to play around that. There are some issues even on the MTL library. The most reliable way, also good for debugging and consistency or whatever, is just like MSL source code into the executables and do JITting compile when you actually run Eerie and then want to create the compute pipeline, stuff like that. Descriptor set and the pipeline layout is more like schemas for describing compute pipeline resource boundings. Like, okay, this kernel requires 2 input, 1 output. The input 1 is at set 0, bounding 0. Input 2 is at set 0, bounding 1. Output might be set 1, bounding 0, something like that. Gives us a way to actually telling the driver this executable and are needing these resources, and you are not telling the exact resources, so you can swap the data resources and make the executable and the compute pipeline being done once and then gotten reused, because under the hood this invokes driver compilers to compile the source string or some IR and JITting it, stuff like that. For the descriptor set, it's kind of a working concept. Metal side, the corresponding concept is argument buffers. Unfortunately, on the Metal side, the argument buffer is actually kind of tied to the MTL function, which means you cannot create it before you create the compute pipeline. This is the difference with the whole API, where we want to go with like more do things in advance and plan things ahead, but still like it's bridgeable and we can support that. I don't think I have much time, going a bit quicker. This talk is more on the runtime side, but still want to tell it about the kernel code generation. We have the compute pipeline basically takes in compiled code of the kernels where you dispatch to the GPU. The code compilation on the kernel side happens in the way that it goes through the Eerie code generation pipeline right now and cross compile to MSL. That is pretty much because, I mean, this is a reliable approach, and we don't have public IR available for Metal to target directly. We do reuse all the code generation facilities on the Eerie code generation pipeline and do cross compile to MSL to then invoke the offline code chain for MSL to generate MTL library and then embed that into the flag buffers via MFB. So as said, dual path suppose. So I need to push more on doing more like offline compilation. It is supported right now, but there are some issues I need to further look into it. Regarding next steps for the whole, I think functionality-wise, we want to push for compute side, reusable command buffers, and then on like memory and also compute side, especially on memory side, async allocation, deallocation is not yet implemented. And then, as mentioned before, the management of kernel and the pipelines needs to improve. Performance hasn't been a focus thus far, especially on code generation, but we share the Eerie code generation pipeline. All the stuff we added there just naturally translates here, but we might need to actually get a proper configuration stuff to guide towards generating code better for Metal and Apple GPU architecture and stuff. Runtime side, as said, the structure of the whole guarantees we have clean surface, and we are not doing too fancy stuff under the hood when implementing the Eerie whole. So most of the time is coming from like the real driver and stuff, and we plan. The goal is trying to do big picture stuff and do advanced planning, the reuse and all this stuff. So it's not a top concern for now, but we certainly need to perform and measure and then improve when the use cases arrive. This is a bunch of resources. Ben did a really great talk about Eerie runtime design overall, which also covers the whole side, like various concepts. I touched base on that with concrete examples and how things are implemented on the Metal side, but I would still very much encourage you to listen to the talk. The runtime side hasn't been changed hasn't been changed much structurally and architecturally. So information there is still very much relevant, even it is like 2021 or something. I kind of forgot when it was recorded. And then the whole Metal whole driver code is like, you can find it in the same directory. There is a README there, sort of like as a documentation of all the major pieces, how they are mapped and stuff like that. And also each example from the user's perspective, how you can call into this to actually do ML and do other use cases. So that's about it for today's talk. I used up all the time. I was hoping to go quicker. Scott?
So how are the performance profiling and debugging tools for Metal? Is it kind of comparable to what we've done with Tracy and NVIDIA Nsight? Are there gaps for compute workloads that graphics workloads don't suffer from?
You use Xcode for sure as a one stop for everything. I haven't played with it extensively. I have markers added for the whole side in Metal. You can actually get Tracy profiles of it too. So I think you can use both. For like internal to the GPU driver, like the kernel level information, you need to use Xcode for sure. The thing is like, it's really nice. I mean, the profiler side, you can actually use I think it's profile manager or something. I have that hooked up directly. You can actually generate let me try to go to that. Generate Xcode readable profiles. It's here. Just a moment. Okay, here, MTL Capture Manager, and you can do this command. It will actually give you a GPU trace, and then you can open it with Xcode to investigate all the information. Xcode gives you some suggestions. You can improve here and there and stuff like that. This works even in command line, so very nice. And but I haven't played extensively with Xcode yet, so.
Well, I would say that's actually great timing. So we are pretty much 1 minute before the end. So, Lei, thank you a lot for this presentation. It was very informative and, went through a lot of details. I think for folks that have more questions, let's follow up online on the mailing list or on Discord. And then, yeah, I think we may try and sneak in one more community meeting before the end of the year, but with all the breaks, it gets difficult. So, thanks very much for this presentation, and please feel free if anybody has any more questions to follow up or any suggestions for future topics. Okay, and with that,
Talk to you later. Bye.
Thank you, Lei.